I'm gonna grab the mic real quick. Hey, everybody joining in remotely. Could you give me a thumbs up if you can hear me clearly? Oh. All right, perfect. Thank you.
All right, guys and gals, it's time to get started. Thank you. Ooh, I think that's perfect. So as people are kind of like trickling in, I will go ahead and let them get started because I didn't account for the fact that there would be a long line. So to get the food. So we'll just go ahead and let them go. So just huge thanks for my two speakers for coming, Aryaman and Zen. And these guys are very smart. We've been having some really interesting conversation while we are waiting. And both like Aryaman, one reason I kind of like started following him because he had mentioned sometime on X or Twitter, whatever we call it these days. He had mentioned some point, he's AI, he's going into PhD student on Twitter, and then he mentioned something about having a background in linguistics, which I do too, and I was like, oh yeah, I can follow this guy. So then along the way, he and Zen came up with this new paper, and as I was reading it, I was like, okay, or reading the thread, but this sounds pretty promising. We should definitely keep an eye on this. And so, fortunately, when I reached out to them to see if they would be willing to come, they said, yeah, let's do it. And this is their first external talk on this topic. So, yeah, should be pretty interesting. And so, and like I told them, and I told you guys earlier, the last guy we had, his project has really taken off and gained a lot of popularity, and so we hope yours does too. And we'll see. Maybe we can get this the video published later out externally and stuff, so they can start, beating the bushes and spreading the word and stuff. So with that, Aryaman is, I think you said, what was your major? It was linguistics, CSN linguistics. But Zen, his undergrad was actually aerospace engineering. So that's kind of cool. And Zen's a second year PhD student, and Aryaman's a first year. And so, like I said, I really think this is a great topic, and I think you guys are going to love it. And I'll leave it to you. There you go.
Okay. Yeah. Thank you so much for having us. Uh, yeah. I mean, I have not given like external talks before, so this is new to me, and I'm very, very happy to be giving it here. It seems like a nice audience for us. And yeah, so I'll just briefly introduce ourselves. So I'm Aryaman. Uh,
I'm Zen.
yeah, and we'll be introducing representation fine tuning for language models, and we call it ReFT because everything needs an acronym in our field. Yeah, so this was like we were working on this for the past 2 months about, and this was work with we have our master student Zhengxuan on the paper and Atticus Geiger, who's also at Stanford. and recently graduated, and of course our long list of advisors between the two of us. Cool. So then we'll start off.
Yeah, so I guess I will start. Yeah, thank you all for inviting us to give a talk. This is our first talk, and also this is first time presenting these slides. So if you have any questions, feel free to stop us. And
Thank you guys for coming.
yeah, no problem.
Thank you.
Okay. So I'll quickly go through some headline results of ReFT. So ReFT stands for Representation Fine-Tuning. It is a new approach to parameter-efficient fine-tuning, not just as a variant of LoRa, adapter, etc. I will try to explain the details, but in the hindsight, we're trying to learn the edits to the representation to achieve a task objective. ReFT is also built on top of representation editing work from interpretability. So it's grounded in a lot of interpretability research that Aryaman and I did in the past. Distributed alignment search, representation engineering. I will try to cover some of those core concepts in the later slides. And ReFT overall, it matches or exceeds the performance of SOTA PEPT with much less parameters, training parameters. Okay. So this will be the outline of today's talk. I will first go through the background. I will introduce the ReFT, and then Aryaman will talk about the results and discussions. So let's maybe go through a quick overview of parameter efficient tuning methods. So PEPT methods. So we have prefix tuning. So essentially, we're adding some learnable embeddings to each layer or to a couple of layers, and try to just tune on those embeddings to achieve the task objective. So that's the prefix tuning. It's very lightweight, but if we look at the performance overall, it's worse than adapter or LoRa approach. And then we have adapters. So this is a simplified version of adapter, but essentially we're adding this learnable components, which is additional components to the models. So in this case, it's a transformer model. So I'm trying to simplify here. We are adding an adapter layer in the middle of layer 1 and layer 2, and everything else is frozen for the model, but we just tune the adapter layers to achieve the task objective. So that's basically adapter. So this one is specifically a serialized adapter. So it's adding into the middle. People also use parallel adapters, which I'm not going to cover here. Then it comes to LoRa. So LoRa came out 2022, and it basically catch a lot of attention. So what LoRa did is slightly different from adapter. It learns a weight diff that can be applied to the original weights. So if we look at in more details, this is the input to the LoRa layer. So the input originally is X. With the original weights, it will calculate some hidden representation as the output. What LoRa did, it's basically learn a low rank approximation of a weight diff, which it names it as A and B, and it will calculate basically a sort of an intervention or a representation edits that applies to all the positions based on the weights. So I guess I will also try to show the comparison between LoRa and our approach, but essentially LoRa learns this very thin weight diff that try to change the representation across all the layers and all the positions. And it seems like out of those three, LoRa still stays the state of art, give most of the state of art performance, and there are obviously more and more LoRa variants coming out very recently. So when we're doing this ReFT project, Aryaman and I also find out like even for 2 weeks there will be a new variant of LoRa coming out. So it's very competitive fields. But yeah, I guess takeaway here is that those SOTA parameter efficient tuning methods usually target model weights instead of the representations. So I think that's the main difference between PEPT and ReFT. So let's before we talk about the ReFT, let's maybe look at the representation view of the PEPT methods, right? So as I talk about, the LoRa learns a weight diff that's applied to existing model components, and eventually it will apply to all the representations across positions and across layers. If we unroll it, essentially, if we see the input token representations, let's say for transformers, then LoRa basically do representation edits across all the time step and across all the time layer by applying this very thin weight diff. So that's the summary here. So PEPT change representation across all the time step. So we basically ask the question, whether these two phrases are actually necessary. So by updating the model weights and across all the time steps. What if we just learn a set of interventions that applies to representation and actually apply to a few representation only? So what if we can do this by training with less parameter, but achieve the same task objective? So that's the central question we are asking. So what we're doing is that we learn a set of interventions that gets applied to representations only across a few time steps, and to achieve the same, task objective. So let me give more detail about the intervention we are learning here. We parameterize the intervention by this phi function, but this phi function can be any function that you would like to design. In the paper, we provide a very specific instance of it, which we call low ref. We parameterize this phi function by using two low-rank matrix. So it gives less learnable parameters. The phi is basically intervention function with learnable parameter that gets applied to certain layers and certain positions. With that, I will quickly introduce ReFT. ReFT has this phi function, and the phi, we need to apply phi to certain positions, so that's P, and then we also apply phi to certain layers, so that's L. So basically, we are learning a set of interventions that contains those three main hyperparameters: the phi function, and the positions we get to apply the interventions on, and the layers we get to apply the interventions on. So this picture shows like we apply two phi functions to different layers and different positions. Basically, like with the concept of ReFT, you can sort of design any phi function you want and then apply to any position you would like. Yeah. Yes. So I will discuss a bit later, and also Aryaman will discuss that. But yeah, so basically the intervention we're doing is only for the prompt tokens, and then we find out that if we intervene on either the prefix or suffix alone, it's not that effective compared to intervene on the prefix plus suffix of the prompt token. So that's kind of one trick. We sort of see the intervention of the prefix as sort of like an anchor intervention, which will adjust the information readout of the prompt tokens, and the suffix intervention as sort of like a generation intervention, which will steer the model behavior. But yeah, we didn't actually verify it, by looking at the representation stuff. But yeah, so position and layers, those two are new hyperparameters that we need to tune for ReFT, which doesn't exist for LoRa. But for the phi function, how we actually parameterize it. As I mentioned in the paper, we actually provide one specific instance, which we call low ref. And the design of low ref is inspired by our previous interpretability research work called distributed interchange interventions. So it stands for DII. DII is an interpretability tool that intervenes on the subspace of the representation and see whether the information, whether causally informative concepts or lives inside the representations. So the most causally effective subspace of DII can be found by using gradient descent. So we basically learn to find that subspace that will causally manipulate the model output behavior. That's where the I guess the low ref, the specific variant of ref that we that's why we came up with that low ref variant space. Okay. So yeah, so this diagram again shows the core concept of DII. We are doing interventions. So we take some representations among a forward pass of a model run, and then we can run through the DII and then plug into another forward run of the model pass and try to manipulate the model behaviors. Yes. I think it's quite vague, but I'll try to be concrete by showing the actual math here. So this is how the DII will run. So the B stands for the B and S stands for the base and source representations. So when we're doing the interpretability research, we think like if we want to verify a representation encodes some causally informative concept, that we will run like two inputs through the model and then try to intervene among those two inputs and get a controlled output behavior. So that's that's what we call base and source representations. And with the DII, we also learned this rotation projection matrix, which is an orthonormal role matrix that will project SMB into this linear subspace. And by doing the minus here, we're essentially doing interventions among those two. Like we specifically swap the linear subspace from source into the base. So that's what this formula is doing. In the high level, it's like we are modifying a linear subspace, or a concept lives inside the linear subspace of the representation, try to change the model behavior. Yeah. So yeah, you can also see B as the original representation, and then this part as the editing vector that we try to edit in the linear subspace. I think Aryaman will talk more about this later. But yeah.
Yeah. So there's probably a lot of math, but I'll try to go through it. Yeah. So basically, what we're trying to do in interpretability is like, if someone says that, oh, I think this part of the model stores this information. So it could be like the model is keeping track of if the user is happy or not based on their question, or something like that. Anything high level. We don't have ways to verify that claim like so far, because you train a model, it's totally uninterpretable. There's some math going on inside, but it learned how to do everything itself. So this whole approach, the purpose of it is like saying, okay, if someone claims this thing, what we're going to do is like, if you claim the information is here, we're going to like screw with the information in there based on some alternative input. And like, if it changes the model's behavior, that's proof that the information was stored there. And if it doesn't change it, then that means, the model's not tracking that. Yeah. 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 Yes. Yeah, exactly. Yeah. So it's all about like causality. So in the past, people were doing like, they're training a second model to figure out what the first model is doing, and then you don't know if the second model, like how that works either. So that was complicated. But this is probably like the simplest thing we can do to verify if a claim about the model is true. So I'll make a distinguishing, like I'll try to distinguish these two. So a model has weights. The weights define the function that the model applies. When you feed some input, that function gets applied to each part of the input that produces representations. So what we're concerned about is like, what information is in this representation? Because humans can't read it. It's just a list of numbers, right? Like we don't know what's going on internally. Yeah. Yeah, so that's where this whole intervention thing comes in. So for example, like if you want to know, like, oh, is the model keeping track of the customer query being happy? What you do is like, you'd come up with an input where the customer is happy, an input where the customer is unhappy. And, if some information is stored somewhere, you can swap in the unhappy version into the happy version without knowing what's going on inside. You can just swap something. And if it has an effect on the model's behavior, you know that it's there, right? Yeah. Uh-huh. Yes, exactly. Yeah. So this test is only for verifying. Yeah. So in practice, when you actually want to run this, it's slow. You got to check every position. Or like with this stuff where we want to find a linear subspace, then you got to check every subspace or come up with a faster method. So yeah, that's one of the ideas we've had. Yeah, but interpretability is just, it's slow, it's inefficient. That's just where we are right now. Yeah, so we'll talk about one thing where, so with this subspace thing, you can actually learn it with gradient descent. So that's one thing you can avoid. Yeah. Yes. Yeah, you're very right. Yeah, we don't have guarantees actually. So basically what this tool gives us is like, it's a way to verify a claim, and it's like a subset of claims you can make about the model. And honestly, this is like, I think the best anyone has so far. It's just a very, very hard problem to figure out what's going on inside model. Yeah. Yeah. So we do think in the long run, you can train something that tries to figure out the best solution for this. But yeah, interpretability is just hard. We're like, yeah, we're deep in the math. We're doing linear algebra, and this is like best we came up with. Yes. Yeah. So in practice, we found some cool stuff. So for example, like sentiment, like, whether a sentence is like a positive review of a restaurant or a negative review, that stuff gets localized at the period, at the end of a sentence. You can find like, is it happy or sad? But obviously internally inside the sentence, it's sort of harder to track what's going on. Yeah, and then stuff like linguistic features, which are stored on individual words, like is this singular, is this plural? That's also easy to find localized. But yeah. Well, basically, we're pretty early, I would say, on this kind of work. And I think it can get much better. But yeah, that's our interpretability background.
Instructions. So what we call like for the results like find by DI, we call that abstractions. So not like we are verifying the information that's encoded there, but it's an abstraction of a high-level causal model. Then when you do intervention, you know how the model will behave. So it's sort of different. It's like the information is encoded there, but we also make sure like the information is decoded by the upstream model computation in the way that it's controlled by the interventions. So whatever we're discovering here, it's more like a switch inside the model. Like you can switch on or switch off, or you can steer the model to a certain direction. There's no like structural guarantees. Like, okay, the high level model we're discovering is like match exact transformer computation, or like the high level concept is actually encoded in that specific, representation at a certain layer. It's more like the representation plus all the upstream computation match the counterfactual behavior we're expecting. So.
Yeah. Okay. Yeah. So the interpretability stuff, that's hard. This is like the best tool we had for it. And then we were curious, like, can we adapt it? So this is a very powerful thing we can do inside the model. You can turn a switch on and off that controls some behavior in the best case, like if you find something that works. So we were curious, like, can we use this for non-interpretability stuff? And so we basically just fiddled with the equation to do that. Yeah. So can you go back? Yeah. Uh, yeah. So originally when we're doing interventions in interpretability, we want like a base and a source. So like a good thing and a bad thing. We want to be able to swap the bad thing into the good thing, make the model believe it's not a bad thing, like that kind of thing. And that requires pairs of stuff. But when people fine tune their models, they don't give us pairs. They just say, this is the good thing, and like make the model do the good thing. So we had to sort of get rid of this one equation in the term. So all we did there, yeah, so this is the source representation. We just replaced this with a linear transformation of the base. So this could be like the model sort of comes up on its own, like this is the bad thing, and this is what I want to change, or the opposite, Yeah, basically we let the model learn, and it works. So that's yeah. Cool. Yeah. So this is the final equation, and I don't know how much this means to everyone, but like this is a very small modification of existing interpretability stuff, and that's what we really want to emphasize. Like we didn't come up with something totally new. This is grounded in existing work. Yeah, and then that also raises the question, like, why this particular equation? So in the paper itself, where we tried a bunch of different appellations where we changed different parts of this equation in different ways, and like our conclusion is it doesn't actually matter like what the form of the equation is, as long as there's enough learnable components in the equation that we can learn how to modify model representations to make it behave a certain way. And that's just like the whole idea is powerful, and it doesn't matter like what specific phi function you use. Yeah. Yeah, and then so we talked about the intervention function. So the other thing that remains is like, where in the model should we apply this function? Like there's like you run a model on a long piece of text, there's so many tokens, there's so many layers if it's a big model, like GPT-4 or something like that. Like where should we screw with the model to make it behave the way we want? And so our approach to this sort of was like, we'll come up with an engineering solution. We're like, we want to edit the minimal number of things that we need to in order to make the model behave a certain way, because we don't want to impose extra runtime costs for the user if they want to use this method. Yeah, so like we talked before, existing fine-tuning methods, they edit every position in the model by editing the weights themselves. And that's like, yeah, but we think only a few positions are necessary. It's not like you need to, when you're fine-tuning a model on like math or something, you don't want to change how it reads English, right? Like these are two separate things. The model already knows some things. We only want to make small tweaks to its behavior. So what we do is like, instead of applying at every position, we pick a few positions. Now, which positions we do it at, that's an engineering problem. And so we'll talk about how we address that. So one thing we know from language modeling is like, if you edit the model internally while it's doing its forward pass, it's running its computations. Once you make that edit, it affects everything downstream. So like if I edit the model's behavior at the first word of a sentence, that's going to affect how it produces the second word, third word, so on. Like that propagates. So that suggests like, okay, let's only edit the prompt, because the user hands us a prompt. We make edits to the internal representation of the model on the prompt. That will affect the model's response downstream. So that's one way to avoid extra costs, because when the user gives you a prompt, that's all processed in one go. Versus when you're producing outputs, that's like one word by one word. So yeah, this is cheaper. And then inside the prompt, one issue is that prompts can be indefinitely long. So a user might give a query with 2 words or with 100 words or 1,000 words, and like we really don't want it to be super expensive when the user gives us a long query. So our idea was like, okay, for each prompt, we can look at like the first P tokens, which we call the prefix, and the last S tokens, which we call the suffix. And that's like a fixed length. We'll only look at like first few words, then the last few words. And a consequence of this is that like now we've made the cost totally fixed. So if the user hands us 1,000 words, we'll only edit the first 10 and the last. Or they hand us 10 words, that's fine. We'll just edit the whole thing. The cost is fixed no matter how long the prompt input is. And we think this is super important because from an engineering perspective, like people use LoRa or adapters or all the existing fine-tuning methods out there. LoRa is successful because it's really cheap. Like you can add it back to your model and the cost is 0. So we really want to minimize maximize our benefits and minimize the cost. And then another engineering consideration is like, do we want to learn separate interventions at each position, or like one intervention we apply to everything? So that's, again, something we leave up to the model tuner. That's like a decision you can make. It's unclear like what works better or worse. It like depends on the task. Yeah. So the overall summary here is like, we apply our ReFT function to a fixed length prefix and suffix of the prompt that is passed to the model. And this works because, if you edit the model's internal behavior, that affects its outputs later on. And this also saves costs. So there's no added cost when the model is producing its output. You just pay an upfront fixed cost when the user hands you a prompt. We just edit the prompt and like the model continues behaving as normal. It's a very minimal change to the model's behavior. And that's the best we could do, I think, to minimize the added cost of our method. Yeah. Yeah, so like all machine learning methods, we have hyperparameters that like the model trainer needs to set. And this list looks kind of long, but like if you compare it to existing methods like LoRa, there's only a few additional things you have to futz with. Yeah. So, and actually LoRa has some additional parameters that aren't in this list. So overall, we think it's pretty even compared to existing methods. It doesn't seem to be harder to use. It's cheaper, and you get pretty good performance or even better performance than existing methods. So yeah, we were kind of surprised, but like it seems to work pretty well. Yeah. Yeah, sure.
Yeah, now let's look at some results. So this is an overview of the results. I will go through 4 benchmark one by one. So we look at common sense reasoning, arithmetic reasoning, instruction tuning, and typical the glue benchmark in terms of natural language understanding. So let's go through the common sense reasoning. So common sense reasoning, it's also formulated as sort of like an instruction tuning with the instruction tuning template. So we give a common sense reasoning question as a multiple choice task. And the model has to, respond with the correct options. So this, as you can see, through this example, the generation is short, but it requires common sense or knowledge grounding into it. So we tested among 8 common sense reasoning data sets, which is a common sense reasoning data sets, formulated all as multiple choice tasks. So this is the performance results. So we compare against with prefix tuning adapters, serial and parallel, LoRa and Dora. Dora is the newest, I think, or the newest and also maybe the strongest variants of LoRa that I currently have right now. And we compare with them in 2 settings. The low reft hours means the hyperparameter is tuned on our own depth set. So it's actually a GSM&K math data set. So we took the hyperparameter there, which actually has a certain, has a slightly longer training epoch. Training epoch is 6. And get that condition give us the best results. But we also tune it with epoch 3, which is quite standard for the LoRa. So for epoch 3 condition, we tune it with 3 epoch and with this batch size 16. So that actually exactly matched the Dora and LoRa condition. So avoid being, since we see the data sets multiple times, then it could be just that could be the one confounding reason why LoRa performed better. But if you look at both conditions, LoRa at epoch 3 or LoRa at hours with our hyperparameters, both are significantly better than Dora, and also LoRa, and with much lower parameter count. So that means for common sense reasonings, for tasks like this, ReFT methods, or specifically low ReFT instance we're testing here, definitely give the best performance and with much less training parameters. Next, we look at arithmetic reasonings. So this one, it's I think it's quite different from common sense reasoning. For this benchmark, it's GSM&K or other math reasoning benchmark. The model not only need to generate the final answer, but also it need to generate the chain of thoughts. So you need to generate a long form chain of thoughts before landing on the final answer. So this one you can think of like we're learning a steering vector that needs to be very precise in terms of math reasoning, since we're only training intervention on a prompt token. So this actually, I would say it's like quite hard for ReFT to work. And actually, yes. So based on empirical results, we are also for the 13B model, we are close in terms of performance compared to LoRa. Again, with much lower parameter count, but again, we are not seeing that significantly better thing as we saw in the common sense reasoning. But again, we are only we're training intervention only on a prompt token. So that means like the control power we have is only those steering token we are at the steering vector we're adding into the prompt token. So maybe future research can look at whether we want to add another layer of intervention during the decoding step. Maybe that will be needed for doing the math kind of precise reasonings or precise steerings over long generations. Then we look at instruction tuning. So I think this is the surprising results that we have, right? So people usually do just throw a instruction tuning or preference data sets and do SFT on it, or do RLHF or DPO. But here we actually look at we find out that we only need to fine tune a very small number of model parameters to make a base model an instruction following model. So this is one example. We are doing the evaluation using Alpaca Eval v1.0, and we are doing the instruction tuning on the Llama 2.7b base model with this ultra feedback data set, which is a pretty high quality, a couple months back. Okay. So this is the results. If we look at, we also compare with Llama 2.7b full fine tuning on the same data sets, and Llama 7b LoRa, and Llama 7b RED. So RED, it's a new variant of a bit fit. You can think of like it learns a bias term as well as a scaling term. So it's also very low parameters. So we compare with these two. And RED stands for the SOTA, I think, in terms of the parameter count and instruction tuning performance. So as you can see, LoRa just being significantly better than RED or LoRa by just tuning 0.0039 or 4% of the full fine tuning parameter count. So this actually pretty surprising. So that means to make a base model instruction follower, you only need to tune like very little parameters. So that also means the pre-training phase of the language model gave all the knowledge to the language. And instruction tuning is more like a style transfer to make, not just a next token prediction agent, but make an instruction following agent. So it's more like a style transfer thing. Because, I don't believe like we just need to tune these parameters to give new knowledge to the base model. Yeah. Oh, yeah. Go.
Yeah, so I would say in fine tuning, the main cost is memory, right? So when you want to full fine tune a model, the memory usage is like 6 or 8 times more than like just running the base model by itself after you've tuned it. And so yeah, and that's like if you don't have a big GPU, then you can't train a big model. So training time itself, the main cost in training time, even when you use LoRa, when you use any of the parameter efficient fine tuning methods, even ours, the main cost comes from running the model itself. The new parameters we add are like really tiny costs compared to that. So I would say in training time, actually, there's not a huge difference. Yeah, one thing is like we have this orthogonalization on one of the matrices, which slows down training a lot. But then we also have experiments where you get rid of that, and that speeds it up, and there's no effect on it. So I would say the main benefit you're getting is like the memory cost is low. Training time is like, yeah, like it depends on the task, I would say. It's less, but it's not like 10 times less. But it seems we have some additional experiments where you run on like you just tune on a really small data set and you can get good performance, which isn't possible with LoRa in some instances. So yeah. Yeah. Yeah, so it's data efficient. Yeah, and I think I should also emphasize like this was definitely the most interesting result. So like when someone trains a language model from scratch, you don't get anything useful. You get a big autocorrect engine basically, like it or an autocomplete engine. It just gives you the next word. And to make it usable, there's this whole stage of like you have to collect a bunch of human questions and human responses, like from question answer websites, where you pay humans to give you these results. And then you have to tune the model on that to make it behave as if it's a person that responds to questions. And like, that's very expensive. But like with our method, it turns out you don't need to change the model itself a lot to get it to behave that way. Yeah, okay. And our last set of results is not like practically that important, but we had to do it because everyone compares on this benchmark. So yeah, we tune these really small language models on natural language understanding benchmarks, and like, yeah, the scores like match with every other method because this benchmark has been totally saturated. Like this is not that important. But yeah, generally what overall the results show us is that on a wide range of tasks, on a wide range of models, like we can match or exceed performance of previous state-of-the-art methods while using way fewer parameters at training time. So yeah, I think we were very excited by that. Yeah, we have these nice figures which won't show up in full res here. But like if you consider like x-axis is number of parameters, y-axis is performance, we're like on the top left of every chart here. So like minimize the number of parameters and like still get really good performance. So yeah. Yeah, and so along with this work, we released our code, which is more than most academics tend to do these days. Yeah, so we have this library called PyRefT, and you can just like however you train a LoRa, you can pretty much copy paste and change a few words, and it should work out of the box. And yeah, we have a bunch of people filing GitHub issues, so we've been up late like fixing stuff. But yeah, feel free to try it and give us feedback. We're very happy to have users. Yeah, and then there's some additional discussion. So we'll probably go through this quickly because some of these are super academic additional experiments we did that, but yeah, we'll see. Yeah, so one thing was that, so I showed you that equation, which was the phi equation, the intervention that we apply. And like, we just copied and pasted sort of from existing interpretability work. But then, like, there's no reason that that's the best equation. Maybe there's other ones. So I had that whole list of equations that we showed. And we tried like all these variants of the intervention function. And what we see here is like, as long as the number of parameters in the intervention is matched, the performance is like within 0.2 percentage points. Like, it doesn't make a big difference. So that really opens the floor of like, can someone design a better intervention function that's more efficient or something like that? And yeah, overall, I guess that also dampens the interpretability findings of our work, because it means like other things that aren't from interpretability might also work better. So yeah, that's a very engineering-y work here. Yeah, and then we tried some weird experiments. So we were like, okay, can you push down the number of parameters to like the minimum possible, and like how much information can you store with that? So we tried like rank 1, which means like a fixed vector that you learn, you apply to the last position at a single layer. How long of a sequence can it memorize? So for example, we'll just throw like 2,000 words in there. Can you store 2,000 words in this tiny intervention and make the model always respond with that or something? And yeah, so if you feed it Alice in Wonderland, it can memorize up to 2,000 tokens from the text, no problem. And that too at different layers. Yeah, and if you scramble the token, so it's not even like proper English, you can still memorize up to 200 tokens. And then we can also memorize mappings. So like you feed it a dictionary, like here's the input, give me this output. It can also memorize that. So it seems pretty efficient, basically, is what we think. Like if you wanted to tune Arora to do this, you'd need a lot more parameters. And another experiment we tried, so this might be more like practically interesting. So one thing is, because of the linear algebraic constraint we put on the intervention, like all these vectors are orthogonal. That means we can like split up the vector space into like 2 halves and like train each half on a separate task and then combine them together. Yeah, so the experiment we tried is like, okay, let's train half the intervention on sentence completion in German. And the base model is like English heavy, so we'll just feed some German data. And then the second half, we do instruction tuning in English. So what we hoped is like, it'll combine these two, and like someone will ask a query, it'll respond in German. And like, that does happen. So we were pretty impressed by that. For example, like if you ask the question as a user, how do I kill a Linux process? On the German completion subspace, it just puts out a continuation in German that has nothing to do with the query, really. When we do instruction tuning in English, it gives a nice response in English that tells you what code to run to do that. And then if you combine the two, it gives a response in German that like actually responds to the query. So that was pretty interesting, and I think it would be very cool to apply that to like low resource languages, maybe, where you don't have the humans to collect the instruction following data, for example. Or maybe like really niche use cases where like you can't collect thousands and thousands of data set examples. Yeah, and then the final thing we were curious about is data efficiency. So like if your data set is really small, like does this intervention like sort of generalize the stuff that's outside of your data set? Yeah. So basically we like took a data set of like 5, 10 examples, and we just keep training until the loss hit 0. So the output was 100%. And like this seems to work. So for example, we did some instruction following on like the user gives a query, will only respond with emojis. And we have like 5 or 10 examples. We just tune on that like for a while. And it takes like what, a couple minutes to tune. It's really simple. Couple seconds to tune. And it works. So if someone gives a query that's outside of the data set, it responds in relevant emojis. And if you try to tell it, don't respond in emojis, and now tell me about Harry Potter, it still responds in emojis about Harry Potter. So that's pretty cool. And I think it would be very interesting for like like quick adaptation of models for specific tasks where you don't have the money or the resources or the people to collect a bunch of data. Yeah, or like user personalization, because this is a super cheap intervention. Like if your user wants things a certain way, you just collect a few examples from them, feed it to the model, and like you can swap it in and out whenever you want. Yeah, yeah, exactly. If you're serving a chatbot, you don't want it saying good things about your competitor, right? Like put it in there. Yeah, so yeah, we think there could be a lot of practical like use cases of this kind of technology now. Yeah, and I think the broad thing that this tells us is like existing fine tuning, sort of the thing people do where you train a base model and you invest millions of dollars in doing that. And then fine tuning is still really expensive for other companies. Like it's not something you can easily do at home in a lot of cases on the best models. Like there's something flawed there. Like you can get away with doing very little on top of an existing model and still getting the kinds of behavior you want. Yeah. And so thank you for having us. And we have like our chatbots are online. We don't know how many GPUs Hugging Face gave us, so hopefully it doesn't crash when you try to use it. But yeah. So this is the first one here is the chatbot, which is just instruction tuned, so it should respond to queries pretty well. And it only took 18 minutes to tune, so on a single GPU. Yeah, we're on an academic budget, so that's very good for us. Yeah, and then the emoji bot, and then another bot that just refuses to respond to your query. And these were trained in a few seconds. So yeah. There's this demo online called Goody 2, which is a chatbot that refuses to respond to queries and gives like good reasons for that. Like if you ask about a person, they'll say, "Oh, I refuse to give personal information. That would violate their privacy." That kind of thing. Yeah. 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 So really pushing the generalization capability. Yeah, and also our like code is all online, publicly available. Give us some GitHub stars, we won't mind. Uh, yeah, 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 and also all the models we train can be uploaded to Hugging Face easily. So I think we tried very hard to make it useful for the open source community. Yeah, and we train on models which are like tens of gigabytes big. So, if you can get away with only a few megabytes extra, that's pretty good. Yeah, during training, memory cost is very low. Additionally, on top of at inference, yeah, it's just like regular inference, but with a little bit extra. Yeah. So with LoRa at inference, you can just add the weights to the model. So it could be zero additional costs, but then you lose the ability to swap out easily. Yeah. Yeah, you've changed the model itself. Yeah. 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 And because of our engineering decisions, we tried very hard so that the inference cost is like very little. So you just like you can feed 1,000 tokens, 1,000,000 tokens, whatever your hardware can handle. The cost is fixed, additional fixed cost. Yeah. People like they also, but they have this right aspect of to be able to perform this like cat fog and so on and so on. For good intervention, it's hard, so of the team. So you can still just have this like additional like do the catch calculation. And when you're decoding it's all like factor where you kind of layer that each decoding stuff, you also have additional that you're having that single like these parallels for the intervention, you only need to limit like the so people need to have
We can batch for like big batch, we can batch over it. We can do continuous batches, and after we get the big batch, we get this to like all the
Yeah, the batch thing is actually really big. So like we can take in 10 queries at a time or something and process them all together with like it's not more cost than one query as long as you can fit it on your hardware.
and each query can be tied with different basically like different ones. So if user like calling from let's say 10 URLs, each serving different tasks, then they can batch together just do different volume and then like it's a beat like the big task.
Yeah. So I guess that's our whole talk. Like feel free to ask questions, comments, anything.
Three minutes to the next session, so be quick for questions.
Yeah.
More broadly, what's next for you guys?
I guess then get that. Yeah, right. I'm first
Okay. Thanks for putting me on the spot. I think what I'm like really want to see is like how ReFT can help guardrailing the language models. So what we find in the interpretability side is that we find that like if we apply a couple interventions in parallel to the model, the LM actually automatically prefer one intervention over other. So that means like if we do interventions in the model, then we may make model to ignore whatever prompt hacking people are doing. So that's one thing that might work with ReFT. So if we, let's say we train a ReFT to make model generate like safer content, and then we have bad user, malicious user, using whatever automated like prompt hacking techniques that try to come up with weird prompt, weird tokens injected into prompt. We think like it may be harder for those models that are guardrailed by ReFT interventions. So if you put interventions in place into those KV cache calculation, we basically hypothesize like it will be harder to find those prompt hacking techniques. That's one thing that could be interesting to us. Yeah. Yeah. Yes. Right. Especially with those like more recent automated or training based like prompt hacking technique, find those weird tokens automatically.
Yeah, currently what people do is like probably OpenAI does like they get dangerous attacks from they just like train the model to. So it's always like you're playing whack, someone will come up with a new attack, but I train the model for them. Right. Yeah, so I think that's a huge issue in fine tuning, for example. So like practically people get stuff like catastrophic forgetting. Like you fine tune your model on some, something you want it to do and it starts forgetting other stuff because it's being overwritten in the weight space. So I think one advantage we have is we're not editing the model weights. We're adding a little intervention on top, but not modifying the model's mechanisms internally. So I think we should be, at least practically also from my experiment, it seems like other capabilities of the model aren't hurt by doing this. But yeah, I guess you would need better evaluation to figure this out. Like for example, we could train on the math stuff and see if it makes the common sense reasoning worse or something like that. Yeah, hard to evaluate. Yeah, we can just turn off the intervention. Yeah, you could have like, oh, this query isn't the math question, so let's just not apply the intervention. Yeah. Yeah, and with other fine tuning, you can't do that. It's not a reversible process sometimes. Yeah. Any other questions?
No, you guys are late.
Thank you for having us.
Guys.
Yeah, thanks for having us. Appreciate the invite. Yeah, thank you. Great question.
Yeah, I'm gonna make